to our quantum mechanics section, and this is section A. And I will do a brief self-introduction about myself. So my name is, like this old school style. So I will use a little point if you prefer that. But anyway, we will see. Okay. My name is Tian Yu. So it's pronounced as you write Tian and Yu. But if you have a really hard time pronouncing that name, give you an English name, well, very fake English name, it's called Dean. My email address is tliu23@ucsc.edu. If you have any questions, any comments regarding the course materials or regarding something beyond the course materials, I'll be happy to help you and also discuss with you in emails. But if you think your question is so complicated that by only doing emails is not enough for you, so I provide one office hour. This will be a solid time slot. So every Tuesday, starting this week, every Tuesday, 4 to 5 p.m. at the Physical Science Building, 101. So I assume everybody know where is the Physical Science Building, right? And the first floor of that seminar room. But if you have something emergency or emergent, or you make an appointment with me, and sometimes after you come to my lab, and you remember the lab position is PSB in the same building, but in a different room. Okay. So this is one office hour, and I'll also hold another office hour by appointment only. So if you have anything more which cannot be solved here, you can send me email and have appointment. Okay. So before the section of this quarter today, actually, I will give you one question. So think about that. Learning quantum mechanics is what, and put a word into it. What word you can think of to put into it, to express your current feeling?
Energizing.
Energizing. I bet someone is thinking of scary. Some bad words there. I bet. Okay. Okay, we will compare the same sentence initially and after the last section of our course and see whether your feeling will change. Okay, but keep this one in mind and put an adjective into it. Okay. So outline for today's section, mainly 4 parts. So first one about briefly about section policy for this class, and I will followed by this will be the background information about quantum mechanics. So I realize that in our lectures we did not present you much background information for you to enter in this really weird world. So here I want to give you some brief, background or introduction about this subject and why we need to learn this subject. A pretty important subject in PCAM class. And then review 2 things: black body radiation and photoelectric effect, which we extracted in our last Friday. Okay. But one more thing I want to say. So for the section, for the slides, I will make these slides available after all my 3 sections are done. I think probably on Thursday evening, and I will upload this to the e-comments. So there's really no need for you to rush in writing down everything I showed on the slides. So more importantly is for you to focus on what we are talking about and write down what you think are important on your notebook. Okay? And all the things will be uploaded on e-comments. So regarding the sections. So about sections, the first important thing is we don't have quizzes. It's not like last year. Right? But we do not offer any quizzes in before or after sections, but be careful, we have what? When we're going to do quizzes? Pop-up quizzes, and make sure you read the book. And we'll have different reactions if you read or not. Okay? One reminder. Second thing, no attendance recording. So today we have assigned you. That's not for the attendance recording. That's just for people our report. So in the future, when we hand in, we will hand your graded works back to you before or after the session. So I know whose work I should bring here. Okay. So we have 6 sections for this class, and A, C, and D. I will be responsible for that. And actually, you are free to switch to any sections if you want, unless that section can accommodate you. but always notify the section you want to switch from, and the TA of the section you want to switch from, and also the TA of the section you want to switch to. So inform us, and we can bring your work to you. Okay. So that requires you to know who is your TA and who you should contact. Okay. So give you one exercise. Who is the TA of the section you wrote? What is the section today?
C.
A or B? Oh, sorry, what's the section letter for today? A, and who is our TA?
C.
I better nobody will choose A here, right? Okay, so you know who's your TA, and send emails or just talk to them in person. Okay. And about sections, you'll be wondering what we will do in sections. So 3 things. So one, we're going to review the class materials, and that will be the main focus for our sections. And it's not all the class materials, but I will divide into this. So let's say we have consecutive 2 weeks. The first one is week N, and the next one is week N plus 1. So for example, this week is week 2, and we're going to cover the class materials for week 1. So that is black body radiation and photoelectric effect. Okay? And starting next week, we will review all the Monday, Wednesday, Friday course materials. The second thing is we may give you some hints about homework programs. Okay? The first homework program has already been uploaded to economics. And give you some hints if we have time or if you have a chance. The third one is do some practice program, which is closely related to the exam questions. So I have some of the previous final exam or midterm exams, and I will try to adapt some questions from it and put it here, okay, to test your understanding. So that's the main thing, the 3 things we're going to talk in sections. But whenever you have questions, just speak it up, okay, to let me know. For me, I set the requirement to explain something simply, because if you cannot explain it simply, you simply don't understand it. So I believe I understand a little bit about quantum mechanics, but another great scientist turned me down. He is Feynman. And he said nobody understands quantum mechanics. So what I will talk about for this course is a really, really basic quantum mechanics. Really, really shallow level, really, really introductory level about quantum mechanics. So I'm kind of confident that I know something about the really basic things, but when we go deep into it, this is a really huge subject. I maybe know less than you, or hopefully some of you guys know more. I remember last year someone asked me about quantum computation. That's a really, really new technology. So I wish I know. But at that time, I knew nothing about that. Okay? But I will try my best to explain something simply. This class is hard. Trust me, this class is hard, but I will try to explain it in an easy way. But for you, this is a really famous example I gave in manual light sections, is to be persistent. So there are some things that little by little one goes far. One goes far or not depends on the level. Okay? So let's say 1 year, your one level is 1.00. So if you persist the same level for the whole year, at the end of this year, you only get 1, the same as the start of the year. That means no progress. But one thing is, if every day you lose a little bit of energy, just a little bit, 0.01, and you be persistent for the whole year, after 1 year, you get almost nothing. So another situation is, if every day you be more energetic a little bit, just 0.01, and you be persistent for the whole year, you actually get way more than your one level. And guess what? If you get more, you keep for 1 year, you get way more than 1.01. So that's why I want to show you the importance to be persistent, not only in this class, but also in the rest of your life. When you go to work, when you go to anything else. So this class will become harder and harder with the week classes. But I do hope you to be persistent. Never give up in the halfway. Well, hope you do that. So let's start our quantum mechanics journey. So the first thing is I want to start with the daily world you encounter every day, and we call it the macroscopic world. And you know, everything, the motion within this world can be described by classical mechanics, which probably you learn in your physics class, especially in physics 5 and 6. Okay? But the real world, most part of the real world is this part. But there's two extreme situations. The first one is if the substance is moving at the speed of light or just close to that, you know, everything the classical mechanics cannot explain, right? So one example is the mass will increase when the velocity is too fast. So instead we should use Lorentz theory to describe any motions within this world. Have you heard about this Einstein's famous theory? Relativity. Well, have you heard about this in physics class? Okay. Anyway. And another one is microscopic world, which when we're talking about one electron, one atom, two atoms, three electrons. Those things also, they do not obey classical mechanics, and we instead use Lorentz theory to describe the motion. What? Exactly, quantum mechanics. And that's why for the whole quarter of this class, we will talk about this. So as you can see, we actually are entering a really, really different world than the everyday and the daily world you encounter every day. So starting now, I want you to forget about every classical mechanics which you learn in physics. Throw them away. All the things we're going to see is quite different from what you learned before, and also maybe sometimes violate your common sense. Okay, we will see in the future. Okay, so what's new about quantum mechanics or about the microscopic world? For that is we need to solve the problem. What's wrong with classical mechanics in quantum world? Okay, some famous examples, like the first one, black body radiation. And we'll already introduce in the class, so here just a brief review about that. So this is the experimental data, which we measured the energy density coming from a black body versus the wavelength or frequency. So here the figure I shows is in wavelength, but I believe the figure it shows in the textbook is frequency. But anyway, it can be converted. So those data points shows the real experimental data. When they measure, let's say if we have we can measure one wavelength, and we can detect the energy density, and we get one dot. And we keep doing this way, we increase the wavelength, and we measure the energy density, we get another dot. And we do this. And we find that actually there's a peak. And this is the real thing, the real world. It's experimental data. So in physics, if we have experimental data as that, we want to know that anything that behind this which causes this trend or this distribution. So in that case, we need to do the fitting job. And scientists were very interested in fitting this data point. But at that time, before the birth of quantum mechanics, scientists can only fit this data point with classical mechanics, and they developed so-called Rayleigh-Jeans law, derived from classical mechanics. So here, though, is energy density, okay? And here is the user frequency, but anyway, you can convert to wavelengths, and you feed the curve, and this looks like this. As you can see, there's a huge deviation from this part, but actually works pretty good at high wavelength region. But think about that. High wavelength region means low frequency. And remember that? So lambda is the frequency, lambda is the wavelength, and times the frequency nu will give you the speed of light. And speed of light is a constant. So that simply means the wavelengths and frequency, they are inversely proportional to each other. And that means if you reach a high wavelength region, you're actually reaching the low frequency region. Okay, so here in our textbook, they say in the low frequency region, radiation flow works really good. But when going to the high frequency region or low wavelength region, it deviates. Right? And this is for what? Two words. This phenomenon for what?
UV catastrophe.
Exactly. We call the ultraviolet catastrophe. That's exactly the word meaning, the phrase means. Okay? So we say radiation flow field at the UV region. So another scientist called the Wien developed another law from classical mechanics as well, and it's called Wien's law. And the equation is shown as this one. Again, it's rho something versus sweep. Okay? And then feed the data. So interestingly, this time works pretty good in UV region, but then deviate a lot for the low frequency region. And just keep in mind, these two laws are all derived from classical mechanics, and they are not able to feed the data. Because they do not show the peak. So here's the problem. So at that time, scientists did not know what happened. Okay. So the question mark put here. We're going to ask this one soon. Okay. But to answer this question soon. The second one is called photoelectric effect, which we'll also review in class. So classical mechanics believes there's something talking about the light. Okay. So light is wave. It's like a wave of light. And the energy of the light depends on the intensity, right? So we're saying intensity. It's actually not this one. This is called amplitude. A little review from your physics class. So you express a wave function like this, and you have an amplitude, which you express at A. And if you square it, A squared, that will be defined as the intensity. Here. Okay. So classical mechanics believes that the energy of the light depends on A only. Okay? So there's something strange happening. We have a piece of metal for you, and when we shine, this illuminate the red light onto the surface. And we do not see anything. And we do not observe anything. So if we believe that the light going into the metal can actually transfer the energy to the electrons for the electron to eject, then based on the classical mechanics, which believes that the energy of the light depends on the amplitude. So simply if we want to increase the energy of the light, how can we do? Increase the intensity, right? So we're getting more light. So in theory, we will reach a point where we eventually can observe the photoelectrons. But the reality is, we can never observe photoelectrons. Okay? So this clearly violated the classical mechanics. Now something weird happened is, if we shine the UV light with just really low intensity, we will be able to detect the ejected electrons, okay, which classical mechanics cannot explain. Okay. Simply means the energy of the light is not depends on amplitude. Depends on what? At that time. Okay. The third example is the structure of the atoms, especially the hydrogen atoms. And I believe in Chem 1A or 1B, I cannot remember clearly, you learned that the structure of the atom looks like this, right? We have in the center is the nucleus, and the electrons orbiting around it. It's like a planet. It's called planetary model. Okay? But in reality, I will show you some figures, which is the real orbital or the real structure of the hydrogen atom. And let's say maybe this one is 1s orbital, it's 2s orbital, 3p orbital, whatever. In reality, it's like this. This is 2s orbital. This is 1s orbital. This is 2s orbital. This is 2p orbital. It's not a round. It's not a circle. It's really like this. It's a dumbbell. Can you explain it using classical mechanics? Well, something really strange happened. And we will talk about this in chapter 7. At that time, you will know what are this. Okay? They're orbitals, but what are this like shade and the shadow area? There's some meaning in it. Okay? Put the question here. Another thing called Einstein-Bohr debate. They actually quarreled with each other at the early 20th centuries. And what they're saying is Einstein believed that God doesn't play dice with the world. But Bohr says something else. So stop telling God what to do with his dice. And we've been wondering what happened between the two. And we will talk about this in chapter 3. Okay. The final example is the color of quantum dots. I don't know whether you have taken the advanced PCAM lab. In that lab, some of you have synthesized the quantum dots. So quantum dots is like the dots, but within a nano size. So this scale value is about 100 nanometers. So you can say each dot would have a much smaller radius than 100 nanometers, probably just 7 nanometers. So we have several nanometers spheres, okay, which can show something really interesting as the different colors. So if illuminating those particles with UV light, you see this color. But if you turn on the regular light, the aiding light, you will see this color. And basically the colors are different. And this cannot be explained by classical mechanics, because classical mechanics believes the color from reflection. And those are the same materials, okay, just with different sizes. And they can show different optical properties. And this can only be explained by quantum mechanics. And again, we will talk about this in chapter 3 after we learn the five-ring box theory. That theory can perfectly explain the color train here. Okay? So for all of the things, I present you something new in the microscopic world, which all of them cannot be explained by classical mechanics. And instead, they can be explained by quantum mechanics. So anyone who is not shocked by the things happening in quantum world actually has not understand the quantum at all. So hopefully you will be kept shocking during the whole quarter. Okay, that means you actually learn something. Okay. So give you an overview. So after all those questions, let's see what quantum mechanics. What does quantum mechanics talk about? Okay. So here's a picture showing all the famous scientists, including those scientists in quantum world. Okay. And I call this one the all-star team of quantum mechanics. There are many, many famous scientists in which we will learn their theories in our class. But just don't freak out. We will learn something really, really introductory, not something deep into it. Okay. So by introducing those scientists, I want to give you a grand picture of the quantum mechanics. And let's go. So the first one is I test you. Okay. So who's that guy? You have today. Planck. And what's his famous for? In quantum world, in quantum world. We learned. So what? Planck constant, exactly. Planck constant is from what? What radiation? Black body radiation. So remember that? In order to feed those data, we need to assume the inert is quantized. And can be expressed by this equation, where n is integer. Okay, integer 1, 2, 3, 4, 5. Cannot be 1.1, 1.2. For this equation, he was awarded the Nobel Prize. Okay. Second person, I bet you know, Einstein, famous for what? In quantum mechanics. Photoelectric effect. Okay. And he explained that by using photoelectric equation. Again, Nobel Prize. We'll talk about later. What's that guy? Who's that guy? Ford. No Ford. Radford. What? Radford? No. No. You're right. We will not introduce his theory in our class, so that gives you a brief idea. He developed the direct equation to describe the motion in microscopic world. Okay. And he shared the Nobel Prize with another guy, which we'll talk about later. Okay. Who's that guy? Bohr. Bohr is in the picture, but not this one. I bet you heard his name before I finished. Huh? I heard something. Huh?
It's a little unusual.
No. Oh. We have time to play. We have time to play. Well, I bet you must learn that either in gym camp or somewhere in physics, huh? Oh shit, that's so curl, huh? Schrodinger. And famous for what? Schrodinger's cat. That's his kind of something like a thought experiment. But he was avoiding exactly the equation called Schrodinger equation. Another Nobel Prize. And trust me, in the future, especially when we enter the chapter 3, we will keep hearing Schrodinger equation, Schrodinger equation, Schrodinger equation many times until the end of this quarter. So hopefully after this class, we will no longer hear this word. Okay. Schrodinger equation, we'll talk about that in chapter 3. Okay, next group. I bet it's true, you heard his name. And we actually talked about today in the lecture. Bohr? Bohr.
Yes, it is.
I showed him the picture of Bohr before. Yeah. Right. But also we want to get someone with Earth. It's a French scientist. He's a French scientist. Oh, cool. On your notes, if you draw down that guy's name today,
Was his name that's in there?
single name. There's an equation, exactly. That's what he's famous for. Roy. Okay. The Roy is famous for what? Not wavelength equation. You mentioned the wavelengths, that's exactly right. It's the particle wavelengths, or we call it the de Broglie wavelengths. Okay. And the particle way to do it. So lambda equals h divided by p. Again, number 5. Okay. Next one. You learned this theory in gym camp. I think in Chem 1B when we're talking about configuration of electrons. Long time ago, everything lost in your mind. Pauli, exactly. Pauli is famous for what? Pauli exclusion principle, where it says the two electrons with the same spin can occupy one orbital. And in quantum mechanics, we can explain this with this one. Okay? We will talk about this in chapter 7. Again, Nobel Prize. This one. The one in our textbook is the one after de Broglie. And also you learn in Chem 1C or 1B, I believe it's called Rock uncertainty. Heisenberg uncertainty. Okay? Heisenberg uncertainty. Again, Nobel Prize. So every invention, every theory in quantum mechanics in the early time, they were all awarded by the Nobel Prize. Okay. We'll talk about in chapter 1, just right after the Broglie wavelengths. Okay. Okay, this one, that may be hard. You want to guess Bohr? That is close. It's not Bohr, but close. a little bit hard Boyd. And Boyd is famous for his statistical explanation about wave function. And we'll talk about wave function in chapter 3, and we'll talk about his explanation in chapter 4. This one. 4. Yes. Famous for what?
The theory about hydrogen atom.
The hydrogen atom structure. Right? So for his theory, he thought that the hydrogen atom is no longer act as a planetary model, as like rotating. It actually occupies some quantized orbitals with quantized energy, which we'll exactly talk about today. Okay. Number 5 is for this model. So I think that's all for our all-star team of quantum mechanics. And by introducing their theories, actually it covers most of the concepts which we will going to cover in our class. So any questions about that so far? Any questions? Okay, if not, so let's go into the class material, first material review. So the first one will be black body radiation. Okay. So when we talk about black body radiation, you want to know what is black body, right? We need to be clear about that. So can you tell me what is black body?
It doesn't absorb all the wavelengths.
Doesn't absorb.
Or
Or does
emits.
absorb and emits what? All frequencies, or all radiations with all frequencies of radiation. Right? So it's a physical body. So the strict definition of a black body is here. A physical body, which should be a physical body, that can two things. Okay? That can absorb and emit. Absorb and emit. Or incident electromagnetic radiation, or just say radiation, regardless of the frequency or the angle of the incident. So simply means if you give something to me, I will absorb, and I can emit all the thing back. And I can be treated as a black body. Okay. So the question is, does a black body black? Is a black body black? So I know you want to think black body, of course, is something, some body which is black. So everything black should be black body. True or false? So keep in mind, black body is not always black. Okay. Sometimes can be the light, sometimes can be our human bodies. So we cannot say our human bodies are black, right? So anything satisfy this requirement will be treated as black body. But I want to just remind you, the black body, in here we talk about black body is just an idealized body or some model. So in our quantum mechanics, actually we use a field, just use field of idealized body model. So here's the first example. But instead in the thermodynamics, which some of you will choose in the next quarter, we use a lot of idealized models. But in quantum we just use field. So this is just one example. So it never exists in reality. So in our daily lives, we cannot find black body. Okay. So then you may wonder, if we don't have black body, how can we measure black body radiation? Right. So instead, we can approximate something as so for example, the sun, our human body, or something I will show here, they just behave approximately like black body. So what we actually measured is from something near black body. It's not a real black body radiation. Okay. So this one like cavity, what does that mean? So it means let's say a sphere, which is black, can absorb all the things, but with just a tiny cavity on it. So think about that. If there's a beam of light or beam of radiation go into this cavity, and it will bounce back inside, so there will be little chance for the radiation to actually escape from the body here, right? So think about that. It makes sense? So radiation goes into the sphere or into the body and it bounces back and gradually will be absorbed by the wall. So there's little chance for the radiation to escape from the body here. So this body will be treated as a black body. And this is one thing, you satisfy the absorb all the radiations. But once this body is heated at a really, really high temperature, it will start to emit some radiation. And if the radiation it emits actually covers all the frequencies, it will satisfy this requirement. And in all, it will be treated as a black body. Okay. So in reality, the experimental data, the black body radiation we saw before is documented from this model. Okay. We can dig a hole on something hot inside, and it will measure the temperature and the wavelengths from this cavity. And that's how we get that data point. So we call the light cavity radiation. So in the history, we call black body radiation as light cavity radiation. So they are equivalent to each other. So in case you read some textbook which is really, really old, so keep in mind, if they say light cavity radiation, that means black body radiation. Okay. To make sense? First one, black body. Be clear about that, the definition. Okay. I think we have one question in homework. I'll really show you the answer. So here's classical mechanics field in feeding the black body radiation experimental data. Okay. Either Rayleigh Jeans law created the ultraviolet catastrophe, or Wien's law which failed at low frequency region. So we're going to answer this question, what happened? Okay. The question is, it can only, one thing. So if you look at this figure, so this equation works pretty well in this region. This equation works pretty well in this region. So naturally, hopefully naturally, for you may think, if we can somehow combine these two equations together, we might be able to feed the whole data. Right? So if we can connect here with this one, no big deal. That's exactly what Planck saw at that time. So Planck went ahead, combine the Wien's law with the Rayleigh Jeans law, and more importantly, assuming energy is quantized and be expressed in this way, he managed to derive this equation. And guess what? If you use this equation to feed the data I showed before, perfectly feeds the data. And at that time, Planck could not believe this. Okay, so Planck is actually from, he was born here before 1900, the starting of quantum mechanics. So in his mind, he still cannot believe why energy will be quantized. But he still cannot believe that how well this equation can feed this data point. Okay. And here, you may be wondering, why by combining these two and assume, and especially assume this one, can we result in this equation, and why this can feed this data, right? We did not have the chance to copy the class, and nor have time in our section. But instead, I provide you a handout. I actually derived it manually. Okay. But this derivation requires some advanced mathematical skill, which you will probably learn in STANAC, in Chem 163C. But I actually show you the derivation. I show you how, starting from these assumptions, can we end up with this equation. Okay. So if you are interested in this derivation, which is not required for this class, just go check my handout. Okay. So that's Planck's law, this equation. I think for black body radiation, that's the same, you just need to remember. You don't even need to memorize the equation. You just understand quantum mechanics can actually feed the data. Okay. And so one more thing for you to know within this part is the Wien displacement law. Okay. So Wien displacement law talks about black body radiation at different temperatures. So here I show you a picture about this is with low temperature to high temperature. And the thing you can observe is the peak wavelength. So pay attention to the peak wavelength. You have to shift it to what? The left side, right? Do you see that? Right. Shift it. So shift it to lower wavelength region. Right? So lower wavelength region means higher energy or lower energy. Higher energy. So shift it to higher frequency. And this scientist called Wien, remember the mathematics, anyway, derived this equation. So lambda max means the peak wavelength times the temperature you measured the radiation equals a constant, which means lambda max is inversely proportional to temperature, which makes sense, right? If you increase the temperature, the wavelength decreases. And the constant is this number. It's a solid number for every black body radiation. For some, for human body, for the light cavity. They all match the same constant. Okay. This is called the Wien displacement law. So based on this law, can you tell me for the 6 bulbs here, which one has the highest surface temperature? So if I ask you to touch one, which one you don't want to touch the most?
The non-halogen.
The left one has the highest temperature. Okay, let's analyze it this way. Okay, everybody agree we shouldn't touch this one, right? Okay. Wien's law tells you that if the temperature is the highest one, the lambda max will be if the temperature will be the highest one, the lambda will be the lowest one. So lambda reduces, or the wavelength reduces, the color change to what?
Red.
From red to, okay. All right, K1A or K1B. So from red to violet, the wavelength decreases or increases?
Red's 400, right?
Decreases, right? This one is about 700 nanometer. This one about 400 nanometer. Wavelength decreases. How about frequency? Or nu? Increases. How about energy? Energy equals what? H times nu. And what? Increases, right? For this case, if T wants to be the highest T, the lambda must be the lowest lambda. Lowest lambda means what? This region, right? So the color should be either purple, blue, or like violet. Which one? Which one? Looks pretty cold, huh? It's a blue color. But actually the temperature is much higher than the yellow color. So the same thing for your, I think it's a heating panel in your kitchen. If you see something is actually shining like that, a blue color or blue flames, simply indicate the flame temperature is much higher than the yellow flames. Okay. But anyway, never touch those things. Okay. It's not kind of safe.
So are those guys just not hotter because they're more efficient and like producing more light from the amount of heat?
I think so. Yeah, it's something related to the efficiency. They feel like they can save the energy by producing more intensity, and of course high temperature.
But the filament light bulbs are just hotter.
Yeah. But anyway, don't do questions based on your common sense. I'd say because microscopy work doesn't work. Okay. All right. Any questions? If not, let's spend some time and we'll talk about photoelectric effect. Oh, before that, can one review the actual idea here. So the red light has the longest wavelength. Okay, longest wavelength. While the blue light has the shortest wavelength. Or actually, if you have a violet light, it will be short. And the relationship between wavelength and frequency is this. So wavelength times frequency equals a constant. The constant is the light speed, which means the wavelength and frequency are inversely proportional to each other. And wavelength of the visible light is related to color. So if the wavelength is large, or from red to violet, the wavelength decreases. Frequency increases. And based on this equation, the energy of the light increases. Okay?
Can you go back to the graph real quick of the UV catastrophe? Because
UV catastrophe.
well, yeah, I know the graph. Like,
but
if the UV region's at 0.4 times 10 to the 6th, which is what it was, you had the UV catastrophe area was not lined up.
Oh, I don't know. Yeah, it's just like approximately we see that as a UV region. Okay, we approximately see that. It cannot be that really accurate. But anyway, in UV region it doesn't work. Right? At least.
The lines kind of lined up more with the UV at 0.4.
Yeah, because at that time the intensity would be low. You still have some radiation there. to radiate. Or maybe we can talk about that in a second. Okay. But anyway, back here, those two equations are pretty important and actually derived from your K1. So bring them back. I know you lost them for a long time. Bring them back. Okay. So next time, I don't know whether you see that funny picture. If someone asks you what's your favorite color, tell them a wavelength. Or tell them a frequency, or tell them an energy, whatever you want. Okay. So the question? For black body radiation, except that question we can discuss later. Okay, no more. Okay, let's go to photoelectric effect. So as I mentioned before, the classical mechanics failed again in explaining the photoelectric effect. Instead, Einstein proposed another explanation in 1905, so much earlier than he developed the relativity theory. So he instead believed that light is wave, he believed that light is made of photons, which is kind of particle. And so in that case, we have a sun and a sunlight. So if we examine the nature of the sunlight, there are two ways. So for classical mechanics, we believe this is radiation. It's just magnetic wave, the electromagnetic wave going propagation in that direction. But in quantum mechanics, according to Einstein's explanation, is made of those particles, and this particle is called photon. Okay? And the second thing is more important. The energy of the photon depends on the frequency only. It's not, or the energy of the light. Okay? Does not depend on intensity. It instead depends on frequency. And that's the equation you learned in K1A, or exactly here. Okay? For each photon, it carries 1 unit energy. And that energy can be calculated by Planck constant times frequency. Okay. So actually all the energy you feel from the sunlight is coming from each photon. Each photon. And with each photon carries just a single unit like this one. Okay. Cannot carry 0.5, 0.2. It must be 1, 2, 3, 4. Those integers. Okay. Which again means that the energy of the photon is actually quantized. Or the energy of the light is actually quantized. Another quantum mechanics comes. Okay. So based on this explanation, we will see why we can explain photoelectric effect. Okay, why? So this is a piece of metal. And the metal, especially the surface, will have some the free electrons. Right? You learned in your gen chem that the structure of the metals actually involves those positively charged atoms and with the electron C. Right? They can migrate through either to the surface or to the inner part. They're free, they're not free electrons, but they're electrons in the lattice of the metal. So let's say Einstein proposed that the energy can only be transferred between 1 photon and 1 electron. Which means 2 photons to 1 electron, not acceptable. 2 electrons to 2 photons, not acceptable. It must be 1 photon interacting with 1 electron. Let's see what happens. So we have 1 photon with this much of energy, okay, the violet light, and heat on the surface of the metal. And based on this, the energy will be transferred from this photon to this electron. But keep in mind, there's something like attraction force inside, some Coulombic attraction between the electrons with the metal atoms. This is something like someone wants to invite you to a party in downtown, but let's say your parents is actually hold you back, and your parents here is called a wave function. It's just one kind of interaction, or the energy within the interaction is defined as wave function. So here, wave function is not a function. Instead, it's a form of energy. Okay? Again, black body is not black. Wave function is not a function. So let's say someone tells you to go downtown, and you feel really energetic. You feel full of energy, and you want to go. But sorry, your parents do not let you go. So what you should do? I don't believe we will choose to stay. Instead, in order to go outside, you need to persuade your parents to let you go. Right? And once you persuade them, you spend energy. But let's say if you are not exhausted after persuading, you still have energy, then you can go out. And that's what exactly happened here. But it's back. If the energy transfer from this photon is sufficient enough to break down the work function, and if the remaining energy of the electron is still non-zero, then the electron can actually go out. And that's why we can detect the photoelectrons in the experiment. Get it? Make sense? Huh? One photon interacts with one electron. And we do that. So that's exactly the equation shows here. But this equation is pretty easy to be derived based on energy conservation. So how? On the left side of the equation is, see what? The E light or E photon. Alright. Let's say let's do this. So E photon is the energy transferred from the photon. But this amount of the energy, part of it is spent on persuading your parents, right? Which is defined as wage of a work function. So we use phi, and also especially sometimes use capital letter phi. And that's the energy you remain, right? Equals what? Equals the energy of the electrons going out. And we can measure the kinetic energy. Get the idea? Derived from energy conservation. So this is the total amount of energy the electron gives you. This is the electron you use. And this is the energy you use. This is the energy you remain. Okay. So EK equals 1/2 mv squared, which you are in physics. Right. Make sense? So if you have any questions, let me know. Okay. So that expands. If we have a read photon, okay, with lower frequency, with lower energy, the energy can actually also transfer to you. But then the energy is not sufficient enough for you to persuade your parents. And you need to stay here. Okay. So no matter you increase the intensity or not, because if you increase the intensity, you simply just increase the number of photons. But keep in mind, the energy transfer is only between one photon and one electron. So no matter you have 1,000 photons keying on the surface, there should only be one photon which can interact with one electron. So that electron can still not go if your energy is not sufficient. Okay? That's how Einstein explained this. Okay? So in a real experimental measurement, if we measure the kinetic energy of the electrons versus the frequency of the illumination here, we will get this straight line. Okay? And we have a question about this figure. So here I give you some hints. The question asks you to calculate this point, the frequency of this point. So the question is, what's the physical meaning of this one? What's the physical meaning of the frequency?
Energy that the photon needs to equal the work function.
Okay. So I will repeat his explanation. What's your name?
Greg.
Greg. His explanation, perfect explanation. So the thing is, starting from this point, we will get the electron. We'll get the kinetic energy of the electrons, right? So here is just a boundary. So the boundary is where the energy of the electron, the energy of the photon transferred from the photon to the electron, is just the same amount of the work function you need to spend. Okay. So in that case, the electrons will be ejected, but still will be held back. So it will just stay on the surface. But once you get a little bit more energy, it will have some kinetic energy and you can go outside. Understand that? So here, this point related to the kinetic energy of the electron is 0. It's still 0. But this is not just an ordinary 0. It's a special 0 because if we increase the frequency a little bit, we start to observe the kinetic energy. So that's actually the boundary condition, the critical condition, or the threshold condition. And we call this as the threshold frequency. The zone 0 which equals wave function divided by Planck constant. Okay. From here. So we define work function equals h nu 0. So nu 0 is called the threshold frequency. So if we divide the work function by Planck constant, we get the threshold frequency. Okay? That's how you're going to use in your homework. I think the last question is asked you to calculate this number. Okay. Make sense? So hopefully you can finish the homework, at least the last question. Okay. Okay, and let's do one exercise. See how much time we have. Well, we still have more than 10 minutes. So introduce a background. So when illuminating a piece of metal foil using a green radiation, we cannot detect photoelectrons. So the question asks you to determine which way or which ways. So pay attention in the future. If you see some questions writing this way, that simply indicates the correct answer could be just one, could be two, could be three, could be all of them. Okay, really tricky. Determine which ways shown below could possibly result in photoelectron ejection from the same piece of metal foil. So we do not change the foil. We talk about the radiation. Okay. So understand the background? So simply means we have a piece of metal and we shine green light, no photoelectrons. But how can we observe photoelectrons? Ask you to choose. Okay. So there are A, B, C, D, 5 options. And give you 5 minutes, and we'll talk about that after. So keep in mind, could be just one correct, could be more than one. So if you need the photoelectric equation, like this. It may help you in showing this work.